We'll start a new topic now. We're going to look at neural networks. We'll be looking at neural networks today and for a good part of next week, if not all of it. So just to kind of take stock of where we are and what all we've seen in the semester. We've seen different learning algorithms. We've seen decision trees. We've seen perceptron, AdaBoost, and various kinds of ensembles. We've seen SVMs. Most recently, we saw logistic regression. Along the way, we saw many different general principles of machine learning. The idea of overfitting. Multiple different ways to ask the question, what does learning mean? We looked at mistake-bound learning, where we are counting mistakes. We looked at pack learning, which deals with concepts of sample complexity and such things. When we were looking at pack learning, we looked a little bit more carefully at this question of choosing the right hypothesis space, VC dimensions, the expressiveness of hypotheses and all that. And this difference between training error and generalization error. Training error is something we can measure. Generalization error is something that we care about. And we've talked quite a bit about loss minimization and in particular, regularized loss minimization. We looked at Bayesian learning. One thing I did not put here is least mean square regression or regression in general, but that also shows up in the cluster of learning algorithms that we saw. Another principle that we saw, which I don't have here, is the idea that once you write down loss as a once you write down the objective function that you want to minimize, the most common family of algorithms that are used in modern machine learning involve gradient-based optimization, in particular, stochastic gradient-based optimization. All of these produce linear classifiers, except for decision trees, which can produce nonlinear decision boundaries. The common assumption that we've had across everything that we saw in the class this semester was someone gives you the right features. Someone tells you what features work for this task, or it's up to you to come up with some feature transformation that just happens to work. Or another way of asking this question is, we assume that in the features that are given to you, or maybe with some transformations, your hypothesis is a linear function or a linear threshold function, and that is sufficient to represent the problem. Where did that assumption come from? How could that possibly? How could that be? How could life be so simple? So the question that we have to think about is, where do these representations come from? I'm using the word representation as an alternative for features. How do we get the right representations for your problem? That's a good way to think about neural networks. Rather than coming up with representations by thinking about them and coming up with the right features, why not make the problem of discovering the right representation a learning problem? Thinking along those lines opens up the doors to neural networks. So in this unit, we'll be looking at what a neural network is. It's not a new hypothesis class. It's a new family of hypothesis classes, all of which have a similar sort of a design. For this entire family, just like with any new hypothesis class, you should ask yourself, how do you make predictions and how do you do training? So that's what we'll spend a fair amount of time. How do you predict with a member of this hypothesis class? And how do you train with these functions? And we'll spend some time talking about practical concerns. That'll be a little bit light compared to the actual set of practical concerns there are with neural networks, because neural networks are, to put it mildly, a complicated class of functions where empirical considerations matter a lot. And I'll spend some time talking about that, but I will point you to references for more reading. We're not going to complete all of this today. We'll start maybe the first point and maybe the second one, and we'll see how far we go. So let's start with what a neural network is. what the class of functions are, and what kinds of mathematical functions they can express. We've seen linear classifiers, and this is like a cartoon version of a linear classifier that has 4 features and makes a prediction. So you have 4 features, x1, x2, x3, x4, and each of those features, the way to interpret this sort of a diagram, you don't see too much of this anymore. This is how neural networks were drawn, I don't know, maybe in the 1950s. So x1 is a signal that travels along this wire. And when it travels along the wire, it gets multiplied with that weight W1, and so you get W1 x1 here. When x2 travels along the wire, W2 x2 shows up at that thing, you add it up, and so on. When the number 1 travels along this wire, you get plus B. So really, this is W transpose X plus B. It's just a rather convoluted way of writing the dot product. You get that quantity, it's a number, and then I apply a threshold and I get a label. This is just another way of thinking about a simple linear threshold unit. I personally think it's much nicer to write it in symbols, so you have sign of W transpose X plus B. For this class of functions, we saw many different learning algorithms, and the common thread across all of them is you write down a loss function and you minimize the loss. Turns out the same thing also works for regression. For regression, this object does not exist. You take a dot product and that's the output. And you can write down a loss function and you minimize the loss. Seems to be a common theme here. But one thing that we did not address is, where do these input features come from? How do you know what the right features for this task are? So rather than thinking about where these features come from, we could ask, what if these features were actually outputs of a different classifier? Maybe x1 was a feature that was produced by some other classifier whose inputs were or not x1, sorry. The features that went along this wire here were produced by some other classifier. The features that went along each of these wires were produced by some other classifier. Essentially, we have the inputs, the observations x1, x2, x3, x4. We separate them from the final decision rule. And maybe you create a neural network, sorry, you create a classifier that takes the raw inputs, and it's another object of a similar sort of a shape that produces this feature that goes here. You can do that for each of these features. And what we get is a 2-layer feed-forward network. It's just a name for this. Why are there 2 layers? You can think of you have a layer here of predictions and another layer of predictions here. What's going on here is you have a input layer which consists of the raw input that gets mapped into a hidden layer that produces the best features. Imagine that somehow magically you have the best features here that produces the best features that are necessary for this classification task, so that in this new feature space, the task is linearly separable with just one threshold unit. So you have the input layer, the hidden layer, and the output layer here. The hidden layer learns a good representation so that the output layer can succeed. A dot product followed by a threshold, something that we called a linear threshold unit before, represents a single neuron. It's called a neuron. I'll define this a little bit more formally as we go along. And in this picture, there are 4 neurons. There's one here, and each of these represents a neuron. So there are 5 neurons, 4 in the hidden layer and 1 in the output layer. There's an obvious question here. I have these 4 hidden neurons. How do I know that the features x1, x2, x3, x4 are good features for those 4 hidden neurons? Maybe they're not good enough features. Maybe you need to learn their features from the raw observations. Well, you could introduce a separation between the input and the hidden layer and introduce another hidden layer. So now you can have x1, somewhere here you have another set of neurons that create the feature, a vector that serves as features for each of these things, which then serves as features for the next thing. There's an obvious question there. Why stop at 3? Maybe, how do you know that this new hidden layer is the right, has the raw inputs have the right representations? And you keep doing this, and suddenly you end up with 1,000-layer networks. And 1,000-layer networks are considered not too big for today by today's standards. So this is like a high level, just not very formal introduction to this topic. Let's try to formalize this a little bit more. Neural networks are perhaps the most robust approximators of functions that we have today. They can approximate real valued functions. They can approximate discrete valued functions by using the same sort of strategy that we use for logistic regression by producing a probability and then thresholding. They can approximate vector valued functions. They just produce, you have many output nodes. And these are maybe by today's, as of 2025, maybe the most effective general purpose supervised learning methods that we have at our disposal. They are especially helpful for data where that's complex and hard to interpret and hard to even come up with good features. It turns out neural networks shine in those kinds of domains. For example, if your inputs consist of audio and video or text and such things, where you don't know what is the right set of features for the new task that you care about, well, might as well make the task of the representation learning, the task of producing the right representation, a learning problem. It's such an important idea that it has essentially changed the face of machine learning in the last about 15 years, to the point where you have machine learning and deep learning, which is essentially the use of machine learning with neural networks, is sometimes treated as its own field. In fact, there was a conference called International Conference on Learning Representations, ICLR, which came into existence around 2013 or 14. So by conference standards, it's a relatively new conference. And it has now very quickly become one of the most important conferences in computer science, because that's the conference where this question of how do you learn the right representation is most often, that's essentially the focus of that conference. It has become basically a de facto machine learning conference. The most important, one of the most difficult questions in machine learning is, how do you know the right representations for learning? And addressing it directly has led to many of the innovations that we hear about in the news. But turns out underneath all this, there's also some interesting and important algorithmic foundations. Importantly, one particular algorithm, the backpropagation algorithm, has allowed for mechanizing the process of learning. We'll talk about that later on, but it has allowed us to use neural networks effectively with gradient-based learning, in particular stochastic gradient and its variants. And it has allowed us to build these libraries like PyTorch and TensorFlow, which do not know about the application where this framework is going to get deployed. You don't need to customize your code for the new application. You don't need to be deriving gradients by hand. Backpropagation will do that for you. You know your homework, right? Your logistic regression, where I've asked you to derive the gradient of the logistic regression loss function. Basically, backpropagation could do that for you. So among other things, it can also do homeworks for people. Whenever you see neural networks, one of the first things that comes to mind in pop culture is the fact that in our brains, we have neurons. So there are biological neurons. This is the first person who actually who was able to draw. This is the first drawing of brain cells by Santiago Ramon y Cajal. It's more than a century old. Um, mm, Neurons are part of all animal, uh, um, just, I guess all animals, most animals, I don't know. And they have things like dendrites and axons. I'm not sure what they are because, frankly, modern artificial neural networks are only loosely, very, very loosely inspired by biological neurons. There are many, 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 many fundamental differences. So I would strongly encourage you not to take these similarities very seriously because mathematically, the kind of functions that we are going to talk about are very, very different from the kind of functions that um, exist in our brains. So uh, let's not worry about the because brain arguments. In particular, when you see someone talking about AI and hyping neural networks up and saying that it works because that's how the brain learns, for me personally, that's a sign that I should not take them very seriously because they are not sure of it's not clear they know what they're talking about. I shouldn't say that. Anyway, let's talk about artificial neurons. Formally, a neuron is a function. It's a function that takes a collection of inputs. In other words, a vector. Let's call that x because we've been calling that all the way, throughout the semester. And it takes that vector, it applies, it has that function has its own weights internally. It applies a dot product to those or between those weights and the input vector x to get something that we've seen before, W transpose x. It adds a bias term, p, so you get a number. And then it transforms that number using maybe a nonlinear transformation. That transformation is called an activation. So the output of one neuron is nothing but an activation function applied to W transpose X plus B. And now I'm writing the B explicitly because for some reason that seems to be the convention in the neural network universe. We've seen this before, right? We've seen something that's very much like this before. In fact, a linear threshold unit is a single neuron that uses something called a threshold activation. A threshold activation is nothing but so let's call that, I'm going to call that activation of Z. If Z is greater than or equal to 0, then it gives you a 1. If Z is less than 0, it's a -1. That's a threshold activation. Alternatively, I can even think of this as not exactly the same, but also the sign of Z. Then you get a 0 or a 1. In either way, it's a nonlinear transformation applied to that score. That's just one of many, many possible activations that exist in this literature. So here are some activations. We have seen the sign function. That's the linear threshold unit. There is an activation that says, you give me a number, W transpose X plus B. I take that number, the function takes that number and does nothing to it and returns it. That's basically the function that is the identity transformation. For reasons that are a little bit confusing, sometimes this is called the linear unit. If you want your neuron to produce a real number, a natural thing to do is to use the identity transformation. Basically, it takes the dot product and produces the dot product. Another activation that we've already seen before is the sigmoid. The sigmoid is this function that looks like this. It takes a number and squashes it between 0 and 1. A popular activation that shows up in the literature has been showing up since increasingly a lot more since 2011 is something called the rectified linear unit. It takes a number and checks. If the number is positive, it returns it as it is. If the number is negative, it sets it to 0. So it's max of 0 comma z. Another activation is the tan h. Tan h, if you don't remember it, you've heard of tan h, I hope. If you don't remember the shape of it, it basically takes a number and squashes it between -1 and 1. It looks something like that. It looks exactly like the sigmoid, just a slightly wider version of the sigmoid. These are just 4, 5 different activations. There are many, many different activations that exist in the literature. Sometimes you see sinusoidal activation. Don't use them too much because they are too non-convex and they create problems. You see Gaussians, you see polynomials, you see all sorts of interesting activations, but most of the time you see something that looks like this. If you want to, a pictorial version of this, if you have Z, the linear activation just takes the input and produces the output as it is. It's this line. This threshold does something like this. If the input is positive, it converts it to a +1. If the input is negative, it converts it to a -1. Importantly, the threshold is not differentiable. You have the tan h, which is a soft threshold. Looks pretty much like a threshold, except it's differentiable everywhere. You have a sigmoid, which you've seen before, and there are other activations that exist. In particular, one that's useful to keep in mind is the ReLU, rectified linear unit, which is the same as the linear thing on one side, and it's 0 on the other side. Any questions about this? All we have seen is what a single neuron is, and the fact that a neuron can have different kinds of activations. One useful thing to note here is, except for the threshold, every one of these is sub-differentiable. There you can have a subgradient of all of these activation functions, and that becomes extremely important as we go along. Now that we've seen what a single neuron is, let's see what a neural network is. A neural network is a function that's completely defined by a directed acyclic graph. It's a function that maps inputs to outputs and is defined by a directed acyclic graph. A directed acyclic graph now has nothing but a bunch of nodes, and there are the edges between them have arrows, and there are no cycles. You're not allowed to have nodes, edges that go back, for example, because then you get a cycle. It's very important that you are not allowed to have cycles, because if you have cycles, then you can't use backpropagation. We'll see why later. Nodes in this directed acyclic graph correspond to neurons. Every node is a neuron, which means it has its own weights, it has and bias and such things. And the edges carry information from one node to the other. So in this picture here, this node is a neuron, and its inputs are these two values. This node is a neuron, and its inputs are these two values. This node is a neuron, its inputs are these two values. You can construct complicated functions this way. Each neuron is exactly the same sort of an object that we saw before. It gets its inputs, a collection of them, applies a dot product, and it has its own activation function. Sometimes these nodes are organized as layers. So you have an input layer here, you have a hidden layer, you have an output layer, and not because the picture gets very, very ugly, I'm showing a general direction of all the arrows, all the edges point upwards. And every edge is associated with a weight. So that means this object that I've shown here has as many weights as there are edges in this graph. Every edge is associated with a weight. The neural network is completely specified by defining three things. We need to specify the structure of the graph, what the nodes are, how many nodes there are, how they are connected to each other. Every node is a neuron, which means every node needs to have an activation. So we need to specify what the activations are. And every edge corresponds to a weight, which means we need to specify what the edges are. If you give me a graph, the layout of the graph, how the connectivity, if you give me all the activations associated with every node and all the weights, then you have a complete neural network. Usually, when people talk about learning neural networks, they split these three things into different parts. The structure of the graph and the choice of the activation function, together, they are called the architecture of the network. And often this is not learned, this is predefined. As a designer of the neural network for a task, you basically think hard about the task and you say, for this task, I'm going to use this particular architecture. These many nodes, these many edges, this connectivity, and these activations. The thing that's learned from the data are the weights on these edges. So when people talk about learning a neural network, they often, almost always, assume that the architecture is fixed and the edges are actually learned. The edge weights are learned. Questions? Questions about what a neural network is? Questions on Zoom? Yes.
I guess the point of the activation function is to introduce non-linearity, right?
Yes.
Can you explain why that's necessary?
If you do not have nonlinearity, so let me repeat the question in case you didn't hear it. The goal of the activation is to introduce a nonlinearity, but why do we need a nonlinearity? Now, let's think about what happens if you did not have one, if you did not have the nonlinearity. And it's a useful exercise. So imagine that you have three nodes in the input, and let's say you have maybe two nodes in the middle, and let's say they're all connected all the way through, and I have one node at the top. So, and all the edges point up. So you get arrows like this. Suppose there was no nonlinearity in there. I'll tell you the statement of it now, and then once we come to how to do the prediction, you'll see why this is true. Suppose there were no nonlinearity there, this whole function, it turns out. So first of all, before I talk about anything, I have some x1, x2, x3 here, and I have some y here. Y is a function of x, right? If you did not have a nonlinearity in the middle, y is actually a linear function of x. If you do not have nonlinearities anywhere, then you end up with a linear classifier, because all the linearities just collapse. And you can prove this formally once you see how the prediction actually works. In fact, I will ask you to do that as an exercise because it's a useful sort of a thing to do. The nonlinear, if you did not have nonlinearities, you might as well have used a single layer, a perceptron or an SVM. Turns out, neural networks are one of the oldest ideas in machine learning. Artificial neural networks were defined in this incredible paper in 1943 by McCullough and Pitts. And that paper is truly amazing. They showed how a linear threshold units, by combining them together in interesting ways, can compute any Boolean function. And everything about that paper is amazing. I mean, it came out of the blue. This was just to kind of give you some context here. In 1943, we did not have computers, right? We did not have transistors. We barely had, I think there were like maybe 2 or 4 computers in the world. this was 1943, was before von Neumann architecture was even designed. 1943 was a few years after Alan Turing showed that every computable function can be computed using a Turing machine. This was at the very infancy of computer science. In 1949, Hebb suggested a learning rule that has plausibility, that's physiologically, psychologically plausible. The idea is very simple. Essentially, neurons that fire together wire together. If two neurons keep firing together, the connection between them gets stronger. And it turns out that leads to an interesting learning scheme. We don't see too much of that in today's machine learning, but it was called Hebbian learning. And then in the 1950s, Rosenblatt proposed the perceptron as a learning algorithm for a single layer neural network, a single threshold neuron. The perceptron is nothing but a neural network with just one layer and a threshold activation, and the perceptron really caught on. And Minsky and Papert in 1969, in their 1969 book, studied perceptrons, layers of them, from from the geometrical point of view, and it was a landmark book. I mentioned this before once. It was a landmark book in the sense that it introduced a completely new way to think about these objects using the tools of geometry, and it also successfully, with a few other things that happened in that decade, it successfully eliminated funding from artificial intelligence research because it showed that these things, a single layer perceptron can't even learn the XOR function. If it can't learn the XOR function, it's not going to get to, at that time, as the newspaper reports promised, get to consciousness. There was a lot of media hype around perceptrons in the 50s and 60s. So essentially, research in neural networks really went down in the 70s, but then there was still some work going on. This person called Fukushima studied the mammalian visual cortex, in particular, looking at how the retinas of cats work, and he proposed a certain computational formalism for that, which then Jan LeCun adapted to define something called a convolutional neural network. In the 1970s, 80s, multiple different people invented this algorithm that we call the backpropagation algorithm. Various people invented variations of something we call recurrent neural networks. In particular, the person who invented it is someone called Ellman, but then very quickly others built on top of that. But really, things didn't work. There were all these cool ideas that were proposed at that time. And one of my, someone I know in the research community once told me, if you're doing a PhD in the late 80s and the early 90s, it was almost mandatory that you a PhD in artificial intelligence, it was almost mandatory that students had a copy of this 2-volume book called Parallel Distributed Processing, PDP. Everyone talked about PDP, but everyone knew it didn't work. PDP was just another sort of a buzzword for what we call deep learning today. It has had multiple names: parallel distributed processing, connectionism, neural networks, deep learning. The reason it didn't work was because while those ideas were all amazing, they needed massive amounts of data and massive amounts of compute, and neither of them existed. And then around the 2000s, two interesting things happened. We started voluntarily putting all our data online, and connectivity became really good. The internet came along, things like Wikipedia and Instagram and such things became popular. And Flickr was a big source of image data in the 2000s. And then compute started finally catching up with these ideas. Moore's law grew. Moore's law came to a plateau. GPUs became a big deal. Parallel processing actually started working. And suddenly, the ideas that were proposed in the 70s, 80s, and 90s, convolutional neural networks, recurrent neural networks, backpropagation, the use of various different kinds of activation functions suddenly started working. There's something in the AI literature called the ImageNet moment, which is essentially there's a challenge in the computer vision community for identifying objects in images. So the task is the task essentially is the instance space is images. You get an image, and the label is an image containing an object, and the label is what object is in the image. And there are 1,000 possible objects. It's multi-class classification. Until around 2010 or 11, the standard approach for that involved using these hand-designed features that were developed in the computer vision community and building complicated linear classifiers on top of them, actually collections of linear classifiers on top of them. And then in 2011, there was a paper that came out from Jeff Hinton's group, which used an idea from Jan LeCun on convolutional neural networks, literally just took the data for ImageNet, they trained a multi-layer convolutional neural network, and it was incredibly better than the best systems that were proposed before, to the point where the ImageNet leaderboard, it was a shared community challenge where everyone could submit their predictions and people will be placed on a leaderboard. Every year there's something that happened. And until 2010, the top of the leaderboard was all these variants of something called a decomposable attention model, sorry, not decomposable attention model. A model whose name I've forgotten, which is kind of sad. There was a certain family of models that were considered state of the art, and they had connections to SVMs essentially. And then CNNs came along in 2011, and there was almost a 10-point gap. CNNs introduced a 10-point gap over the then state of the art. The year after that, everyone was using CNNs. The field really changed. And this happened across multiple tasks, multiple applications where pre-neural network, there were some tasks, and then then neural networks started getting applied, and you see huge improvements in performance. Today, the standard building blocks for most machine learning applications are neural networks. There are some new neural network architectures that have been proposed in the last decade. In particular, two interesting ones are transformers and graph neural networks. And along the way, we've also made these networks deeper. Depth is really the number of layers. We've learned more through these wide-ranging community efforts. We've learned more about how to control the optimizers. And all these lessons have kind of fed into each other, and that has led to many, many more applications, including things like your ChatGPT. In this class, given that this is an introductory machine learning class and not a class on neural networks, we will probably not cover any of these things. I'll give you the basic ideas of what neural networks are, how they work, and that should allow you to kind of get into the details of a whole bunch of these things. What kind of functions do neural networks express? We know what kind of functions linear classifiers express. A single neuron with a threshold activation. In other words, a linear classifier is basically, it can draw a hyperplane in the instance space and say one side is positive and the other side is negative. If you have two layers, you can start drawing convex polygons. You can enclose a region and say everything inside is positive and everything outside is negative. With more layers, you can draw unions of convex polygons. You can essentially start putting little circles around regions of instance spaces and disjoint regions and say all of them are positive or all of them have a certain label. And this allows us to specify rather complex functions. But this is just like a cartoon thing. Even in the 80s, we knew that neural networks are exceptionally good function approximators. There's a celebrated result from Sybenko 1989 that said that any continuous function can be approximated to arbitrary accuracy using only a two-layer neural network. Meaning you have an input layer, you have a hidden layer, and all the hidden layers are sigmoids, suppose. And the output layer has a linear activation, so you can produce any real number. Turns out that you can approximate any continuous function to arbitrary accuracy using just that object, using something of that kind. There was a hidden catch there. The number of sigmoids in the hidden unit, then the dimensionality of the hidden layer, to get to arbitrary accuracy could get arbitrarily large. So you might have an infinitely wide hidden layer. So you have, say, some inputs, then you have many hidden sigmoids here, and then you have an output. So you get something, a network that looks like this. And then all of these. But it was still an interesting observation because there are functions inside this function class that can be arbitrarily accurate, arbitrarily expressive. Yes.
Sorry. Which way is Y for?
Oh, my default is up is Y. So this is X and this is a Y. Yeah. But some people actually draw their neural networks down. It's a good question. There was some work from the 90s that also said, to a certain degree, your choice of activation function also really does not matter. There's some, we should take that result with some salt, a pinch of salt, because sometimes it does. Something that you can actually prove, and in fact, that's part of your extra credit question, really, is turns out any Boolean function can be represented by a two-layer threshold network. You should think about how you can prove it. I'll give you a hint. Any one-layer network can represent, sorry, any conjunction can be represented by a one-layer network. Any disjunction can be represented by a one-layer network. A two-layer network is really a one-layer network placed on top of another one-layer network. I'm not going to say more. If you are interested, come talk to me. There's also been a lot of work talk about VC dimensions of neural networks. A VC dimension of a threshold network with E edges is essentially E log E. A VC dimension of sigmoid network with V nodes and E edges is between E square and V square E square. I'm not sure this is particularly useful, turns out, because these numbers are pretty large, and yet neural networks can approximate functions pretty well. One useful thing to try to show eventually is what I said before. If we only have linear units, then having multiple layers does not change the expressiveness. I don't think you can show that yet today, because we've not yet covered how predictions are made. But once you see how predictions are made, that you should be able to show that. Questions? No questions? We have 5 minutes left, and just wondering if I should start talking about the forward pass right now, or I'll give you a clue. I'll give you a high-level hint, and then we'll revisit this on Tuesday. So the act of making a prediction with a neural network is called the forward pass. The act of taking a gradient with a a neural network is called the backward pass. So we've seen what a neural network is. We're going to look at how to make predictions for with a neural network. And rather than giving you the algorithm, I'm going to kind of walk you through an example here, because it's looking at an example makes the tedium very clear. And you'll see that it's actually pretty simple. So let's say you have this neural network here. And I'm giving names to these nodes. Your inputs are X's, your outputs are Y, and the hidden layer, the hidden units are Z. But this is not a complete specification of the architecture of the network, because I've not told you what the activations on the hidden and the output nodes are. So, they also have a bias feature that's always 1. So let's say that the hidden layers have sigmoids. And let's say the output layer has a linear activation, which means the output layer takes the dot product and doesn't do anything to it and sends it out. This is a kind of a network that could be used for regression, because it takes some inputs, x1, x2, and predicts a number at the top. So if you want to use a neural network for regression, you should be using the linear activation. And now it gets a little tedious. So far, I've only told you the architecture of the network. I've not told you what the weights are. So you can't actually do anything with this function yet. So I'm going to use every edge has a weight. So this here says the weight that's going into the output node from the second element of the hidden to the first element of the output. This thing here is the weight that goes into the hidden from the 0th element to the first element of the. Every weight has an address. So this is just a naming convention that I used for this slide. It's not even there are no standard naming conventions here. So I have W out 01 is the weight associated with the edge from neuron number 0 to neuron number 1 in the output. Oh, no, not that. This one here. Neuron number 0 here to the neuron number 1 in the output. Yeah, I also realize there's an inconsistency here. Anyway, so how do you make predictions? We have 2 minutes, and let me go through this quickly, and then we can see if you have questions on this and you can think about it. I'm going to shade nodes based on whether we know the value of that node or not. Let's say you have the input. The input is some values to x1 and x2. That means if you know the values of x1 and x2, we know the values of x1 and x2. We, of course, know the value of 1. So we have that entire input layer. Notice now that if you knew the value of x1, x2, and 1, that means you can compute the value of z1. Z1 is a neuron. You take the dot product of its inputs and apply the activation. So you can compute the value of Z1, which is simply the sigmoid activation, because Z1 was defined with sigmoid of this dot product here. It's really W transpose X plus B, but written in this using the corresponding weights. You know the value of Z1 now. Similarly, you can also compute the value of Z2. You know the value of Z2. Now you know the value of the entire hidden layer. You have everything you need to compute the value of Y. So to compute the value of Y, you apply the dot product and its activation. Well, it turns out that Y had no activation or the linear activation. So Y is simply W11, whatever, this weight times Z1, this weight times Z2, plus this weight times 1, which is the value there. And done, we're done. We predicted the output. Basically, we go layer by layer. For every node, we wait till all its inputs are computed. Rather than doing that, we go from the input layer and then compute every subsequent layer as we go along, and we propagate the information